Hello everybody, and next to the last lecture. So we're winding down. I hope that you looked at the announcements, etc., and see the changes to the schedule. Mostly the removing of Module 4 to give you more time to devote to this assignment, the following assignment, and your Peter Principle paper. So, let us get started here. Give this a shift, right? We're going to talk about central tendency, variance, Z-scores. Oh my God, you say, oh, I hate statistics. And we got statistics light coming at us. And I think one thing that's different is we have statistics with a purpose. It's one thing to learn statistics that you may use someday in the future, but now we're going to learn statistics that we're going to use right away. And this is consistent with what's called just-in-time training. This is something that we did at the paper mill, not something we invented, something we learned from many trainers that had come before us, that the best way to train someone is to train someone right before they have to do something. And so you can see how the homework assignment kind of supports that philosophy, at least in part. Right? So we got to talk about central tendencies, and there's three. This should be no great surprise to you. The mode, which is important to us, and we'll talk quite a bit about the mode. It's the most frequent response in the distribution. And then the median is the middle value score. For example, if there are 11 values, and we're going to do this, the median is the sixth value in that list of values arranged in ascending order. So, and then the mean, of course, is the arithmetic average, if you will. So let's take a look at the median, and why is the median important? The median is important for a couple reasons. Certainly in research it's important because sometimes we want to compare what's the effect of this manipulation on our participants based on their self-esteem level. So we might then measure the self-esteem level of all our participants, array their scores in order from the highest self-esteem to the lowest self-esteem, and then find that median value, that central value. Everyone above that value is considered high self-esteem. Everyone below that value is then considered low self-esteem. And that allows us to look at the effect of our manipulation on two groups, that is low self-esteem versus high self-esteem. So the median is pretty simple, right? This is an example, let's say, of self-monitoring scores. And what we do for the data that has an even number of items, simply average the two middle values. And note, this is because they won't all fit on the slide. This is a continuous column of numbers here, just started next door, so to speak. So in this case, what's the middle value? Well, it's pretty easy to tell. That's the last one in this, and the first one in this column would be essentially the middle. So what we do is 9 plus 9 equals 18. Divide it by 2, since there's two values, and the median of this sample then becomes 9. For data that has an odd number of values, it's pretty easy. You just pick the central value then, right? So it's the median split. We will often want to create subgroups from our sample. For example, how do low and high self-monitors differ on sales performance? Those who are below the median, as I suggested before, constitute the low group. Those on top then, those above, the high group, right? Now, let us consider, though, that the median split is not without its detractors. So we take a look at our self-monitoring scores. Let's revisit this. The lows range from 3 to 8. The highs range from 10 to 18. But let me ask you this. See, the range of the lows is 5 points, 6 points if you will, 3 to 8. And the highs range from 10 to 18. They range over 8. But if we take the scores that wrap around the median, that is... the lowest of the highs is 10, and the highest of the lows is 8. So we're faced now with two groups, low and high, but notice that the boundary conditions, how different is 8 from 10? And the interesting question is 8 compared to 10 more different than, let's say, 18 compared to 14? That is, we may have a greater difference between two highs than we would have between the highest low and the lowest high. I know that's kind of confusing. The difference is actually only 2 points there, whereas within highs we have a difference of 8. So This becomes problematic when we talk about the central values, and they say, well, we can cure this because let's not do a median split. Let's not split this into 2 groups. Let's split it into 4 groups, or let's split it into 5 groups. And there's nothing to prevent you from doing that. Again, though, the closest values between groups are generally closer in distance than the within group differences. So the meaningful differences then might be, we might consider splitting into bands. And the idea of bands is we might take a measure that's got, that's worth 30, 50 points. And we say we're going to cut this into 3 bands. So if a possible score is 0 to 30, we say, well, okay, so 0 to 9, let's make that band 1. 10 to 19, let's make that band 2. And then 20 to 30, let's make that band 3. And what we're saying is that our measure probably isn't sensitive enough to be reliably distinguishing between someone who scores 15 and someone who scores 16. But big picture, we're pretty sure that someone who scores in the 3rd band is markedly different than someone who scores in the 1st band or even the 2nd band. And we better be sure of that, otherwise we probably shouldn't be using the measure because it doesn't reliably differentiate candidates. So the median split allows us to take a continuous variable, split it into 2 scores, right? So the example high versus low self-monitors, right? Lows could simply be scored as 1s, highs scored as 2. So notice what we're trying to do is we're converting the score from the raw number score self-monitoring to the banded score that either indicates low self-monitor or high self-monitor, and mathematically we're going to assign that as a 1 or a 2. And you'll see where this becomes important when we want to try to combine scores given vastly disparate measures and vastly different scoring systems. And that's what we're really about today. So we might split the scale into bands, and we can do so with as many splits as makes sense. So consider that scoring 29 is essentially the same as scoring 30, especially considering a certain amount of measurement error is likely, and we talked about measurement error. No measurement is perfect, right? If a measure actually represents a score that is plus or minus 1 point from the measure. So if someone scores a 28, what we're saying is they scored a 28, but in all honesty, given the reliability and the potential for error in our measure, I would rather call their 28 somewhere between a 27 and a 29. That is plus or minus 1 as kind of the margin of error there, right? So if the measurement actually represents that score, 3-point band is not justified. Is the difference between 29 and 30 meaningful in terms of future observed performance on the job once we hire someone? And remember, that's what it boils down to. Is this a meaningful difference? So what we might do then is create multiple bands, and usually, without getting too fancy, the easiest way to do this, and probably the most straightforward, is to simply have equidistant bands, right? So in this banding example, we have scores, right, that run from 18 to 30. What do? Well, the bands, we've chosen to do increments of 3, right? So 28 through 30 is band 5. 25 through 27 is band 4. 20 through 24, band 3. And then moving on down, 19 to 21, band 2. So what we're saying now is our candidates, we're not going to take the raw individual score. We've converted it to a band score. So now we can array our candidates into 5 groups rather than look at their individual scores. And this is a practical approach to both measurement error, reliability, and, in all fairness, predicting the eventual outcome of performance on the job. Questions about that? So basically what I'm saying is I just want the high performers, the moderate performers, the average performers, the not so good performers, and the worst performers. That would be an example of 5 bands in plain English, right? Now let's move on to the mean. The mean is simply the average score. Our sample can be used to estimate the mean of the population of any given characteristic, right? But that's dependent on how closely the sample resembles the population. The extent to which the sample mean deviates from the population represents sampling error, and that is somehow our sample deviates from what we would expect to find in the population. And that might be a good indication of where are we advertising, where are we recruiting our candidates. If we know that we're using a measure that has been standardized and gives us a mean across a wide population, we use that measure and we note that our mean is demonstrably different than the mean observed in the verifying of the measure, then we have to say, why is our mean different than the mean that's been demonstrated by the use of this measure in the past with larger numbers? And that may be a good thing. That might indicate that our recruiting efforts are quite good. You know, we say, well, you know, we want high self-monitors, and we've demonstrated that high self-monitors will perform better at the position, so we would prefer to recruit high self-monitors. And we figure out some magical way to recruit into that category, high self-monitoring, through the magazines that we recruit in, or the websites, or a recruiting message, or our recruiter communication to potential applicants, etc., potential recruits. All of these then can tell us how we're doing. But let's suppose that we're demonstrably lower on the mean we're using on a measure. We're assured that that measure is something that predicts good performance on the job, and I say, man, this group of candidates, this group of recruits is way below the mean that's standard for this measure, then we have to ask ourselves, what the hell are we doing wrong? So the mean is a simple statistic, but it can give us very straightforward and very useful information in this regard. The means of multiple samples tend to converge towards the actual population mean. Well, yeah, and small samples often increase or cause greater fluctuations than the observed mean. So the mean of the distribution, what are we looking at? Well, in this case, this is the classic bell-shaped curve, right? So we have a nice distribution here, and we can see that the mean just floats along. So the distribution itself, the range of scores within a sample, can remain standard, but the mean can vary. You guys know this. I don't want to reiterate it to any great extent. So let's talk about homework 11, part 1. Using the table below, what are the mean and median scores for 10 candidates on the patience measure? And I'm returning to that patience measure. I kind of find that interesting from you guys with your repertory grid assignment on assessing teaching skill, right? So basically, all you need to do is look at the scores that I'm going to provide you and then fill in those two blanks, mean and median. Now, what's the standard deviation of patience scores? Well, I'm not going to show you how to calculate the standard deviation. You either know how to do this, or you can do it the easy way. You can put the column of scores into Excel, and it should be ready to kind of cut and paste, and you can ask Excel to give you the standard deviation of those. And that would be choosing the range, right, and then using the term STD-DEV, if I'm not mistaken, and that will give you the standard deviation in Excel. And if you don't know how to do that, I'm betting someone on your team knows how to do that. And if you don't, it's time to learn, right? Because Excel is a gold standard in business, right? Excel is the bomb. It is a program without peer, really. So, and many of us, believe it or not, have been using Excel since time began, it seems like. I was using Excel extensively when I was at the paper mill, and I left the paper mill in '96, right? So strangely enough, we've been using Excel for longer than you guys have been on this planet, for many of you, right? Powerful program, effective program. Well, the high and low band boundaries are banded in two bands. How many candidates then are in each band, right? And that's the band based on the median split. So, band, low limit, high limit, and number of applicants in bands. So you fill out the table. So check the assignment. You got the data table in there, and that assignment is in Word. So you should be able to, I think, copy and paste that column of numbers into Excel, if I'm not mistaken. All right. So we've kind of now worked through
the three forms of central tendency, mean, median, and mode, right? Measures dispersion. Let's now look at the variability. Range is simply the lowest to the highest scores in our sample. For example, a sample of self-monitoring scores was a low of 3 and a high of 18 in our previous example. Now, the mean is separate from dispersion, right? That is, as I explained earlier, that the dispersion, the variance, if you will, right, the range, the mean here is the same for all of these samples, but notice the narrower and narrower range. Now, for personnel selection, simply put, at a very basic, which of these, let's suppose these all represent the scores from applicants on a given test that we've given them. This is the array of scores. Which do you think is more useful for our purpose in differentiating our candidates? Well, no. The central, the spread is high. This is probably most useful for differentiating our candidates, right? This distribution, this frequency distribution, is not going to be very useful in differentiating our candidates at all. So if we continue to have samples like this on a measure, we have to consider using it in a different way or replacing it with a measure that generates a greater dispersion so that we can differentiate candidates along this axis to a greater and greater extent. Now, variance calculates the distance of each person's score from the mean of the sample. It's always a positive number because the distances are squared, right? So standard deviation is often preferred here. It's not very useful for our purposes, but it allows us to calculate the standard deviation. So that's what we use the variance for, is ultimately to move towards the standard deviation. I've offered you a shortcut in just getting the standard deviation from a list of numbers in Excel, right? Remember when you had to, did you have to do this by hand? My first stats class, I had to do this by hand, right? They give us a column of numbers, and we had to show our work. We had to actually calculate the variance for each of the scores and then do the math to combine it all. Now the standard deviation is the square root of the variance. The square root of the variance is the standard deviation. Standard deviation there relates more closely to the actual scores of our measure. And the normal distribution curves are 5 standard deviations wide, 2.5 standard deviations below, and the mean. So when we talk about, this would be a great example of an intelligence test, which is a test we're unlikely to use as an IQ test, right? What we would see here then, the mean on an IQ test, because it's a standardized test, is 100, right? And the U minus 3 standard deviations would be 70, and the mean minus plus 3 standard deviations would be 130 in this sample, right? So different measures will yield different shapes of distribution. Not all distributions yield this beautiful standard curve. And remember, if we were testing intelligence, but then we separate it, let's give a typical intelligence test as it is, we know that they're ethnically biased. So if we separate our applicants, we say this is the total applicants, and we separate our applicants into 2 groups based on ethnicity, one that's favored by the IQ test and one that's not favored by the IQ test, what we'll end up with is 2 modes, that is 2 high points. And remember, as we talked before, that's an indicator that adverse impact is probably the result of using that measure. So the standard deviation to z-scores, and this is going to lead to our second homework, z-scores tell us how many standard deviations a score is away from the sample mean. So now what I'm saying is that, wow, we've given people, our applicants, this test, and let's say it's a self-monitoring test for the sake of argument, and we see that based on the scores, with the calculation of the standard deviation, that we have some applicants who are up to 2 standard deviations above the mean, and we have a couple applicants that are actually 2 standard deviations below the mean. Well, what does this tell us? It tells us quite a bit, actually, and let's see how we can use this to our advantage to create a summation of applicant test scores to eventually rank order them across, let's say, 5 tests that they've taken. So the standard deviation to the z-score, z-scores tell us how many standard deviations away from the mean, and you go, well, okay, so if I give someone a self-monitoring test and I convert it to z-scores, I can say they're this many standard deviations away from the central point, right? And then I give them a test on patience, so I get self-monitoring. Now, the patience is done on a different scale than self-monitoring, so the numbers don't have the same meaning from those two scales. But note, the number of standard deviations away from the mean on each scale, that's a number that I can combine, although the original scales were numerically different, right? So a z-score of 2.5 means that someone's 2.5 standard deviations above the mean, and that might be an attractive candidate, right, if that's a positive. A z-score minus 0.75 means that someone's 3/4 of a standard deviation below the mean. So why the hell do we need to calculate z-score? Well, I'm sorry, what do we need? Well, we need a large enough sample. Okay, and this is where it becomes problematic. If we may have to consult historic population central tendencies on a measure if we're using small samples. If we're using our own sample that's large enough of applicants, then we can calculate it together. So we need a large enough sample overall, or access to a previously tested large enough sample where we can derive z-scores from that sample. We need a measure with enough range, and that's the dispersion, to differentiate candidates. The mean of all candidates on the measure, that's the number we need, and the standard deviation of that measured sample. So if we have those two numbers, we are good to go. We're ready to rock it. So how do we calculate the z-score? Subtract the mean from the score. Divide the result by the standard deviation. So for example, a mean IQ is 100, the standard deviation is 15. We see an individual score is 130. So 130, that's the score, minus the mean equals 30. We know the standard deviation is 15, so we divide that 30 by 2. We divide that 30 by 15 and we end up with 2. The z-score for that person then is 2. So now we have their IQ score converted to a z-score. They're 2 standard deviations above the mean. We look at their self-monitoring score, which uses a different scale than the IQ score. We convert their self-monitoring to a z-score, and let's say they have a 1.5 z-score. That is, they're 1.5 standard deviations above the mean. But now notice, we can start playing math with those two numbers, because a z-score has the same meaning regardless of the scale. It's this number standard deviations above the mean. Right? So, which means they scored 2 standard deviations above. What does it do for us? Well, I'll tell you what. I had a student in a couple classes, this class many years ago, along with psychology, creativity, etc. And I still keep in touch with him every now and again, Alex Finarn. So I'm going to cite him. He said, so in effect, I remember he raised his hand and he says, effect, z-scores, what do? They allow us to compare hot potatoes to chilled bananas. And that phrase stuck with me, and I know it's kind of a ridiculous phrase, but it makes the point. How do you compare hot potatoes to chilled bananas? Well, you convert them to z-scores, and then you can readily compare them. So the deal is you can take 2 disparate measures like self-monitoring and intelligence quotient IQ, convert them to z-scores, and now, although their scales differed, you can now combine them mathematically. And that's what we need to do, because what we need for an applicant is ultimately, in our applicants, we want to rank order them in terms of their score on our tests, but we need to be able to combine the information from widely different tests, right? So for example, one might have a top score on a measure of self-monitoring, but might be toward the bottom on a score of self-handicapping, and allows us to then combine those measures to make a score. So z-scores allow us to compare the level of performance on one construct to another. So part 2 then, for homework 11, here's a table of the measures, n equals 28, right? Fill in the table for the 2 candidates below.
So here is, and see how I've got it set up? This is 5 tests that our applicants have been given. They've been given a standardized interview score. Remember that? You learn to develop a rubric to score interviews. Well, you're going to turn that into a standard score. A work product assessment, right? Knowledge test, that's 0 to 100. Problem solving exercise is score 0 to 40. Persistent measure, 1 to 10. Well, if they get a 2 on this, and they get an 18 on this, and they get a 98 on this, and they get a 30 on this, and they get a 3 on that, and we add those scores together, it's going to be meaningless gobbledygook. So we can't add scores directly from these measures. Remember, hot potatoes, chilled bananas. So what do we need to know? Remember what we need to know. We know that our sample of our applicants, standardized interview, we had an average applicant score of 4.1. We calculated the standard deviation, or should I say Excel did at 0.35. We do the same thing for the rest of these. We know the work product assessment, hey, 16.2 mean, 2.8 standard deviation. Your job, now that I've told you how to compute standardized scores, Z-scores, is you take that information and you put it into this table, right? So now we have 2 candidates. We have Dahlia and Christoph, right? And what we're going to do is we see Dahlia's raw score is 3.9. You're going to standardize that score. Christoph's score is 4.4. You're going to standardize those scores. You're going to standardize the score for each candidate on their 5 tests. And then ultimately, you can add that number together. And the big question for you is, who did better? Who should we hire based on our test, Dahlia or Christoph? I know, it really is kind of that simple. It seems complicated, but it's kind of that simple. So basic premise is standard deviation and proportion. Well, I mean, there's some basic principles. What we know is that if a sample is normally distributed, like IQ, or many of the tests that we'll use, we know that 68% of the people coming at us, 68% of the people who take this test are going to score between 1 standard deviation below the mean and 1 standard deviation above the mean. This allows us then to predict how many applicants we might need to see. That is, if we need people who score at least 1 standard deviation above the mean, right, then we know what part of our sample in the past scores at that level, and that gives us an idea working backwards of how many applicants we need to bring in to get the number of people we want who score at that level. So it's about proportions, and we want to be able to get to proportions. So once we understand proportions and we have some experience under our belt, we can say, well, we need to hire 3 people, and that means if we want 3 people who perform at this level, present these types of Z-scores, then we're going to have to bring in 30 people, because we tend to find 10% of any given sample that qualifies to our standard. So we can work backwards. If we need 3 and we know that we get about 10% that achieve that level, right, Annika? Then we know that we need 30. So we just do the math in reverse. So the standard normal distribution have similar shapes but can differ in their mean and their dispersion. What we're looking at then is if we want to standardize each measure, and it's not, I mean, if we want to create a standard normal distribution, we may or may not be able to, depending on our sample size. Less important, but for you guys who love your statistics, you can make this happen. What we see then is the Z-score and the proportion. What we know then, 30% of scores lie between the mean and the standard deviation of the first standard deviation. Right? So it allows us then perhaps to develop cut points. And what cut points are is when we then impose a minimum score on our applicants for them to be considered. So any of the measures that we looked at, if we go back, any of these measures, we may then, for whatever reason, develop, hey, anyone who scores below, let's say, 70 on the knowledge test, they're just out. So any one of these measures can also then have embedded in a cut point, and that is like a no-go point for our applicants, etc. So we have a lot of flexibility in how we want to do this, basic kind of math. We're not talking heavy duty math. Okay, and the proportions allow us to know how many applicants we're probably going to need to look at to get people above the cut point for any given measure. Questions about that? All right, so z-score and proportion then. What we see here is that a z-score of 1 represents a score at the 84th percentile. So what does this mean? What this means is if we give this test to 100 people, then we know that 84 of those people, and notice I'm using 100 because it translates directly to percentages. That is, this z-score and proportion, we know that 84% of a sample, just a random sample if you will fall below 1.0. And again, proportions are important to understand how many applicants. If we have the history of our applicants on a given measure, we had 100 applicants. Hannah, Annika, that is uncalled for. You think that's? I think it's uncalled for. What do you think? I don't know. So what we're saying though is, wow, our cut point on self-monitoring, for example, is 1 standard deviation and above. We're not going to hire anyone lower than that. Okay, well, we need to hire 16 people. I say, well, okay. What that means is I'm going to see 84 people out of 100 that aren't going to achieve that z-score. So if I bring in 100 people, I can expect 16 of them, or are they 16% or 16 in raw numbers, right, that will achieve the cutoff point. So just a brief overview basically of how we use those crazy ass statistical principles that we learned and often don't get a chance to use, and how critical they are for us to be able to rank order applicants when applicants are being scored on multiple and diverse numerically calculated numbers. Ultimately, once we convert each score on each test to a z-score, we're then free to combine those z-scores and create an overall picture of the applicant's quality. Questions? And of course, if you have questions, what are you going to do? I would love to see you in our meeting. So you guys have a good day. Take care, and that's all I got for you. Bye.